Hey guys, welcome to the third molecular orbital video. So this is going to be about talking about the properties of these conjugated pi systems, or like dienes that we talked about. So something like this guy right here, or a longer molecule here where we have three double bonds conjugated to each other. Okay, and we're just going to talk about the properties about their properties. So what's so special about these compounds, right? What's so special about this guy versus, let's say, this one? Right? This isolated double bond. So one thing that may come up, especially in a test question, a lot of times they kind of like to ask, like, select the incorrect statement of, like, they'll give you like three compounds and they'll say like, oh, compare to 2 and 3, 2 can have like blah blah blah. All right. So one important aspect to understand is something called a heat of hydrogenation. Hydrogenation. All right. This is going to be the heat released when we do like this H2, remember, PDC addition. So we're removing the double bonds and turning them into alkanes. And so what is this whole heat of hydrogenation thing? This is the heat that's released when we do the hydrogenation, and it tells us the stability of the compound. All right. And so if we looked at the heat of hydrogenation, right, of, let's say, this butadiene compound right here. So here, like, we have like this graph, right? And that's going to be like the enthalpy, delta H. And so we're going to look at that, the enthalpy of that guy versus the isolated double bond, all right? And I know this may be like, oh, Genchem again. It sounds like a lot like Genchem, but trust me, it's not that bad. It's hopefully it's fairly straightforward to understand. And so it would actually, let me take away the delta. It's just H, actually, just enthalpy. So this is just going to be heat released, right? When we look at the butadiene versus this isolated double bond, right? And here is the alkane that we're going to get when we do the H2 PDC addition. Okay, so if we want to, let's say, take this guy down to the alkane, right? It has two double bonds. This guy only has one, right? So we're going to use two of it, right? So that it's almost fair, right? Two of this guy so that we have total two double bonds, and one of this guy because he already has two double bonds to make it fair. And we look at the heat released, you're going to see that we would expect it to be the same, right? It's overall still two double bonds. It's actually not. This one right here releases less heat. So he has a lower heat of hydrogenation. Okay? This means that he is more stable. Okay? If you have a lower heat of hydrogenation, you are more stable. And so this is a key feature of these dienes, right? And so one question, I'm pulling a part of a question from an old exam, was this. They give us these two compounds. This was compound 1. Actually, yeah, and oh, they didn't even compare that one. Sorry, let me change that. They gave 3 compounds and asked about the stability. Gave statements about them, and you had to pick the incorrect one. So I'm only going to focus on one of those specific choices. This is compound 2. And this was compound 3. And one of the statements was the heat of hydrogenation of compound 2, right, is going to be smaller than the heat of hydrogenation of compound 3. So we're just going to figure out if that's true or false. So we're going to say just heat of hydrogenation of 2 smaller than 3. So true or false. How do we figure that out? Remember, we said how these conjugated pi systems make something more stable. So let's look at the pi systems we have in 2 and 3, the conjugation we have. You can see that these two double bonds right here, they're conjugated to each other, right? I can resonate that guy there and this guy on the carbon and something like that. But this double bond is isolated, okay? So this one is not conjugated to any other p orbitals. So he's by himself. It's an isolated double bond. So we have one conjugated system plus one double bond. In this guy, we still have that one isolated double bond, but then the same thing for these two. They're not conjugated either. I can't somehow resonate this guy here because he has a full octet. So that's right, and there's two hydrogens here. And same goes if I try to do it that way. Not going to work. So we have no conjugated system here. So no conjugation. And we have three isolated double bonds. So remember, conjugated systems have a lower heat of hydrogenation because it's more stable. Therefore, 2, because it is more conjugated than 3, is more stable, and so its heat of hydrogenation should be smaller. All right? This is going to be true. All right? And so this statement would have been considered true. So now that's that's heat of hydrogenation, okay? And so now what are the other properties that we have here with these conjugated systems, right? One of them, another one is what happens when we expose these guys to light. So I'm going to clear this over here. So now we're going to talk about what happens when we expose these guys to light. All right. So what is an exposure to light going to do? So let's draw. I'm not going to draw the molecular orbitals, so I'm going to talk about butadiene, this guy. Right, and if you want to draw the molecular orbitals, feel free to do so. I drew them in the previous video, so I'm not going to do it here. So what I'm going to do is I'm going to just actually focus on like those electrons, like the little lines we drew the electrons. So here was pi 1, pi 2, pi 3. And so we're going to have 2 electrons here, 2 here. Also, another trick to determine the maximum amount of molecular orbitals you have is just the maximum amount of p orbitals. So if you have 4 p orbitals, you'll have 4 molecular orbitals that you can draw. So that's butadiene. And actually what I'm going to do is I'm going to space these out a little bit more. And now I'm going to draw another compound. Hexatriene. All right. So this has 3 double bonds conjugated. Butadiene had 2. And now we're going to draw all those orbitals. No, the electrons at least. You can draw the orbitals if you want on your own. So this is going to be pi 1, pi 2, pi 3, pi 4, pi 5, pi 6. We have 6 total electrons. And so that's how we fill those. Now the last compound I'm going to draw is going to be this guy right here. Let me actually draw that a little better. So now this guy has 4 double bonds that are conjugated to each other. Okay? Butadiene had 2, hexatriene 3, and this new compound has 4 double bonds. So we're going to draw the electrons for this guy, and it's going to go all the way up to pi 8. So let me draw this better. So here's going to be pi 1, pi 2, pi 3, pi 4, pi 5, pi 6, pi 7, pi 8. Sorry, it's a little bit cramped. And so we have 8 electrons here. So we go all the way up to pi 4. Now, what's the point of me showing you guys all this? There's a reason I drew them. I spaced the electrons or these like orbitals out the way that I did. You can see that butadiene with 2 conjugated double bonds, it's much more spaced out than hexatriene and here in this compound. Okay, why is that? Well, one thing about these compounds is that when we expose them to light, we excite an electron. So if I expose, let's say, butadiene to light, one electron jumps up to this new orbital. Okay, so it jumps up that way, and then it's going to, once it jumps up, it's going to drop down again, right? So it goes to pi 3. Now all of a sudden it drops down to pi 2. When it drops down, it's going to release energy in either the heat or light, okay? And so why is this important? Well, again, it gives us another property of how these compounds can absorb light, specifically UV light, and they can ask you this on the test, and I've seen it as before, about how conjugated systems like these, like butadiene, hexatriene, or even double bonds in rings, how I showed you in those that previous example, absorbs UV light. Okay, and so the thing to know is here's the energy between these two orbitals, relatively big. Now here's the energy when we have a more conjugation. You see it gets smaller, the gap. And between these guys, it gets even smaller. So the trend is that the more conjugated of a system you have, the lower the energy difference between your orbitals. Okay, keep that in mind. The more conjugated, the lower the energy difference between your orbitals are. And how does that correlate to that whole idea with light, right? So when that electron jumps up, it gets excited, and when it falls back down to its proper orbital, it releases energy. The less energy we release, the higher wavelength of light we absorb. So usually you see wavelength with this lambda symbol. So let's draw the trend. The higher the energy, the lower the wavelength. The lower the energy, the higher the wavelength. Okay? And so this can help us determine, like, how conjugated our pi system is, right? But they could very easily ask you on the test. So definitely keep that in mind. So you can see that this guy here will absorb UV light at a higher wavelength than this guy because he is more conjugated. Right? Now, one other thing before we stop the discussion about the UV light absorption. If I drew out butadiene, this guy here, right, just regular butadiene, and compared it now to, let's say, this guy over here. All I did is I added an alkyl group, right? How does the UV light absorption change? Okay. If we, because I didn't say it before, the more alkyl groups you have connected to that conjugated system, the higher your wavelength is. So the less energy that electron releases when it drops down. So this guy will absorb UV light at a lower wavelength than this guy, simply because he has more alkyl groups, right? And so an example of that was in that same question I originally showed you guys, there was another statement that talked about these two compounds, and we had to figure out if it was correct or incorrect. So let's try to figure that out right now. This is compound 1 now. And here's compound 2. So the statement was compound 2 absorbs light of a longer wavelength than compound 1. Okay? Is this true or false? So it's saying absorbs longer wavelength than 1. True or false? So remember, we said the more conjugated your system, the longer the absorption of the longer the wavelength it'll absorb, and the more alkyl groups we have on it, again, the longer the wavelength is. Okay. Usually, if you're talking about, say, something with 3 double bonds, right? Conjugation with 3 double bonds versus something with 2 double bonds and 1 alkyl group, let's say, the one with the more conjugation is the winner. Okay. So let's look at these examples. So what's the conjugation in 1? These 2 double bonds are able to conjugate to each other, right? I can, let's say, resonate this guy down. This now comes up. So we have 2 double bonds conjugated. It also is conjugated to this double bond right here, right? So that means all 3 of those double bonds are conjugated. So we have 3 conjugated. Okay, a triene. Now look at 2. What's the conjugation here? We have those 2 double bonds, but now it's not conjugated to this isolated double bond. So we have 2 conjugated plus 1 double bond. So we said the more conjugation we have, the longer wavelength of light will absorb. And so compound 1 is more conjugated than compound 2. So he should absorb the longer wavelength. The statement was compound 2 absorbs a longer wavelength. This is incorrect. And they did ask us for the incorrect statement, so you would have picked this one in that case. All right? And so that's another important feature you should know about absorption of light with these conjugated systems. All right? And so I hope it's cleared it up for you guys. In the next video, we'll talk a little bit more about these things and get into the new reaction you guys are going to learn called a Diels-Alder. All right? See you in the next video.